this video, we are going to work on problem 3.3.9 from the textbook. Consider the Thomy function defined on the interval 0, 1 by the following formula. F of x is equal to 1 over q if x is a rational number given in the form p over q, where p and q here are natural number and p and q are co-prime. And f of x is equal to 0 if x is irrational. Right? So given any epsilon greater than 0, define the set A epsilon by the following formula. A epsilon is the set of all x in the interval 0, 1 such that f of x is greater than or equal to epsilon. And then now we have to show that the set A epsilon here is finite. Okay? And in the second part, we have to show that f is continuous at every irrational number and discontinuous at every rational number. Before solving the problem, let me recall an important tool that we are going to use. That is the sequential criterion for continuity. Consider a function f defined on set D, and let x not be a number in D. Here, D is a subset of the real line. Then f is continuous at x naught if and only if for every sequence xk in D not converges to x naught, the sequence f of xk converges to f of x naught. This criterion is very important, especially when we try to prove that a certain function is discontinuous at x naught. In that situation, if we can show that there exists a sequence xk D not converges to x naught, but the sequence f of xk does not converge to f of x naught, then we can conclude that the function f is discontinuous at x naught. So now we are ready to solve the problem. To better understand this function, let me give some example of computing the function values. Now here, if x is equal to 1 over 4, that is a rational number written in the form p over q, where p and q are co-prime, then f of x is equal to 1 over q. So in this situation, f of 1 over 4 is 1 over 4. Alright? And similarly, f of 1 half is 1 half. F of 3 over 4 is 1 over 4. Okay? Now, how about f of 4 over 6? F of 4 over 6 is equal to f of 2 over 3. Note that here 2 and 3 are co-prime. So by the definition, f of 4 over 6 is equal to 1/3. Okay? So you can see in this graph, f of 1 over 4 is 1 over 4. F of 1 half is equal to 1 half. F of 3 over 4 is equal to 1 over 4. Now, in the first part, we're going to take any epsilon greater than 0. This is epsilon. And we are looking at the set of all x such that f of x is greater than or equal to epsilon. And we have to show that that set is finite. Okay? So let's see how we can prove that the set A epsilon is finite. Now, for any epsilon greater than 0, recall that the set A epsilon is given by the following formula. A epsilon consists of all x in the interval 0, 1 such that f of x is greater than or equal to epsilon. Okay? And observe that f of x is 0 if x is irrational. So this set is actually the set of all x in Q intersection 0, 1 such that f of x is greater than or equal to epsilon. Okay, so it is in fact the set of all rational numbers in the interval 0, 1 that are greater than or equal to epsilon. So it can be written as follows. This is the set of all rational number of the form p over q in the interval 0, 1. Over here, because f of x is greater than or equal to epsilon, and x here is p over q. So 1 over q has to be greater than or equal to epsilon. And p and q here are natural numbers, and they are co-prime. Okay. So this set can be rewritten as follows. This is the set of all numbers of the form p over q in the interval 0, 1, such that from here we can see that 1 over p q is greater than or equal to epsilon. So we can multiply both sides by q and get that 1 is greater than or equal to epsilon times q. That means q is less than or equal to 1 over epsilon. So the set can be written like this. This is the set of all p over q in the interval 0, 1, such that q is less than or equal to 1 over epsilon, and here p and q are in n, and p and q are co-prime. Right? And observe that the number of q in n and q is less than or equal to 1 over epsilon is finite. Okay. For example, if this is just a real number, a positive real number, okay, and we are looking at the number of positive integers that are less than or equal to 1 over epsilon, for sure the number of q here is finite. One example is if 1 over epsilon is equal to, say, 100.1, okay, then there are only 100 natural numbers that are less than or equal to 1 over epsilon. They are 1, 2 up to 100. Okay, and also p over q is less than 1 because p over q is in the interval 0, 1. We see that p is less than q and less than or equal to 1 over epsilon. Right? So the number of q such that this condition is satisfied is also finite. Okay? Therefore, we can only form a finite number of rational numbers of the form p over q such that this condition is satisfied. Therefore, the set A epsilon is finite. So we finished the proof of the first part. Now we are going to work on the second part of the problem. We're going to fix any irrational number A and show that the function f is continuous at A. So we fix any irrational number A in the interval 0, 1. Then by the definition f of A is equal to 0. Okay. Now we are going to apply the definition of continuity in order to show that f is continuous at A. To do so, we have to show that for any epsilon greater than 0, there exists delta greater than 0 such that the absolute value of f of x minus f of A is less than epsilon whenever the absolute value of x minus A is less than delta, and x is in the interval 0, 1. Okay, and note that a here is 0, okay, and f of x is non-negative. So this is just f of x, okay. And also, this condition means that x is in the interval a minus delta, a plus delta, okay. Now, we are going to use the first part in order to prove the second part. We fix any epsilon greater than 0, okay. By part A, the set given by this formula is finite. Okay, so a epsilon can be written as r1, r2 up to rn, where each ri here is a rational number. Okay, so this is a finite set. I can represent it in the number line as follows. So this is 0, this is 1, this is r1, r2 up to rn. Okay. Now a here is an irrational number, so a doesn't belong to this set. So, for example, a is here. Okay. Now, since a doesn't belong to the set a epsilon, we can always find delta greater than 0. Such that the intersection of the interval a minus delta, a plus delta with a epsilon here is the empty set. Or equivalently, this interval is a subset of the complement of a epsilon. Okay, so how can we choose this delta? We can choose this delta, for example, by taking the mean of the absolute value of a minus ri, where I runs from 1 to n. Okay, then for sure delta satisfies this condition. Okay, now from here we're gonna see the following. For any x in the interval a minus delta, a plus delta, and x is in the interval 0, 1, we see that x cannot be in a epsilon. And so, because x is not in a epsilon, f of x has to be strictly less than epsilon. Okay, and as you know, this is in fact the absolute value of f of x minus f of x. Okay, so to summarize, if we take any epsilon greater than 0, we prove that there exists delta greater than 0, such that the absolute value of f of x minus f of a is less than epsilon whenever x is in the interval a minus delta, a plus delta, and x is in the interval 0, 1. Therefore, the function f is continuous at a by the definition of continuity. Now we are going to show that f is discontinuous at every rational number, and we are going to use the sequential criterion for continuity. Okay, so now we can fix any rational number r in the interval 0, 1, and r is written in the form p over q, where p and q are natural numbers, and P and Q are co-prime. Right? Then f of r by the definition is 1 over Q. Right? Now, by the density of the set of all irrational number, we can always find a sequence of irrational number not converted to R. Okay? So let Sn be a sequence of irrational numbers in the interval 0, 1, not converted to R. Okay, again, this sequence does exist by the density of the set of all irrational numbers in the interval 0, 1. Okay, then we're going to see the following. The limit of f of Sn as n goes to infinity is equal to the limit of because f of Sn is equal to 0 for every n. So this limit is equal to 0. Okay? And as you know, f of r is 1 over q. So 0 is not equal to 1 over q. That is f of r. So we have found a sequence Sn in the interval 0, 1 not converted to R, but f of Sn does not convert to Fr. Therefore, f is not continuous at R. Okay, and therefore the proof is complete.